Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Centre at the National College of Ireland. And this short video is it's another video in our series dealing with probability. And this one is going to introduce our basic counting formula, I suppose from an empirical perspective, with respect to calculating the probabilities of events with respect to some outcome. Okay. And the rule we're going to say is something like this. So here's our first rule. Okay. So our first rule, okay, it's going to be something like this. It's that the probability, okay, of some event relative to some sample space. In the previous video we defined that the sample space was just a set of all possible outcomes, and that an event was some subset of that particular set of outcomes. So the rule is going to say this, is that the probability of some event, read in that way, if I was to read this is the probability from a notation perspective. What is the probability of some event? Well, it's equal to two numbers. It's a fractional amount. It's a relative frequency is really what we're defining here. Okay? It's equal to the number of favourable outcomes, okay, in our sample space or our outcome space divided by the number of possible outcomes. The number of possible outcomes in our sample space. Okay. So let's have a look at some examples. And when we get to the addition and the multiplication rule, these rules are going to help us to simplify some more complicated scenarios and experiments. More importantly, they're going to help us to simplify things back to this basic counting rule. So let's have a look at an example. Okay. And in this case, let's call this example 1. Okay. So in example 1, what we're going to do is we're going to flip a single coin. Once again, we don't know what the outcome is going to be, but we'd like to hazard a guess of what the likelihood of that particular outcome is. Okay? Don't forget the sample space for flipping a coin is heads and tails. Okay? So I'm interested in what's the probability that when I flip a coin that the outcome is a head. Okay? Well, the answer to this question can be got from rule 1. Okay? Where it says what we need to do with respect to the sample space, okay, is we need to count how many favourable outcomes there is in the sample space and divide that by the number of possible outcomes. So in our situation here, well, first I suppose the number of possible outcomes is there's 2 things in the sample space, so the number of possible outcomes is 2. Now, how many things are favourable? How many things in our sample space, and this is a very small example, how many things in our sample space match this particular event here or this condition? How many things in our sample space are heads? Well, there's only 1. So really what we have here now is this, and I'm sure everybody sort of knew this, is that the probability when we flip a coin that we get a head is either 1 in 2 chance or a 0.5 probability of that happening. What's the probability that when we flip a coin we get a tail? Similar argument. It's the number of favourable outcomes, which is 2, divided by the number of possible outcomes. Well, there's only 1 tail in here, so it's 1 over 2. Okay? In this example, I'm going to just keep doing this for a while. What we can see is in this example, that the sum of all the probabilities is, well, a half plus a half is equal to 1. Okay, let's keep that in mind for a moment. Okay. Example 2. Okay. So example 2. Okay. This time we're going to roll a die. So we're rolling a die, and I'm interested in the probabilities. Well, let's consider some. Well, the sample space for rolling a die are the numbers 1, 2, 3, 4, 5, and 6. So the question is, when I roll a die, what's the probability that I get a 1? Well, symbolized, it's when I roll a die, what's the probability that when I roll a die that the outcome is 1? Well, it's equal to the number of favourable outcomes divided by the number of possible outcomes. The number of possible outcomes in a die experiment is the size of the sample space. There's 6 things. The number of favourable outcomes is how many things in the sample space are 1s? Well, there's only 1 of them. So you have a 1 in 6 chance. And you can see what's happening here. The probability that when we roll a die that we get a 2 is also equal to 1 over 6. The probability that when we roll a die that we get a 3 is equal to 1 over 6. And so on and so forth. The probability that when we roll a die and we get a 6 is equal to 1 over 6. And like what we had earlier on, when we sum up them probabilities, sum of the probabilities, well, we have 6 1/6, which gives us a total value of 1. Okay, that's a rolling a die experiment. Yeah. Let's continue with the rolling of a die experiment. Let's do something else. In that experiment here, we were interested we were interested in, let's call them atomic events, the basic building block of our subsets, yeah? The 1, the 2, the 3, the 4, the 5. So let's call the next example, example 3. Okay? So example 3. Okay? And I'm still interested in rolling a die, so I'm rolling a die. The sample space hasn't changed. Its S is equal to the values 1, 2, 3, 4, 5, and 6. Okay? But this time, the event of interest that I have is, well, what's the probability that when I roll a die, I get an even number? Okay? Well, from our rule, it's the number of favourable outcomes divided by the number of possible outcomes. Now, in the coin toss or in the rolling of a die experiment, the number of possible outcomes is there's 6 possibilities. Okay? The number of favourable outcomes is how many things in the sample space match this condition, match this event. How many things in the sample space are even? Well, there's 1, the 2, the 4 is even, and the 6 is even. So there's 1, 2, 3. There's 3 possibilities. Or you have a 1 in 2 chance of getting an even number when we roll a die. What's the probability that when I roll a die that I get an odd number? Well, similarly, go back to our counting rule, which says it's the number of favourable outcomes divided by the number of possible outcomes. So when I roll a die, okay, the chance of getting an odd is, well, there's 6 possible outcomes. There's 3 odd numbers in this particular set, in the outcome space, or the sample space. A 1 is odd, a 3 is odd, a 5 is odd. So there's 3 things in there that match the condition. So that's 3 over 6, which gives us 1 over 2. Once again, when we sum up the probabilities of all the events, yeah, we end up with 1. Okay. Let me do one more, yeah, okay, because this doesn't always add up to 1, yeah. So let's say we're interested in what's the probability, okay, that when I roll a die, yeah, that I get an even number. Okay, once again, we know it's 1 over 2. What's the probability that when I roll a die, yeah, I get a number, let's say greater than or equal to 2? Well, there's 6 possible outcomes. How many numbers are greater than or equal to 2? There's 1, 2, 3, 4, 5, which gives us 5 over 6. Now, in this case, the sum of all the probabilities, yeah, is not equal to 1. Well, a half represents 3/6. 3/6 plus 5/6 gives us 8/6 in total. 8/6 is not 1. Okay? There's an important point here, yeah, and the point is this. Okay, is that when we consider events, yeah, okay, that happen with respect to a sample space, okay, and when the events are mutually exclusive, okay, that means that they share nothing in common, yeah. Okay? So you're either a head or you're a tail, okay. But also, not just that we consider mutually exclusive events, when we consider all mutually exclusive events, in other words, when we exhaust all possible events, yeah, with respect to a particular type of condition, so it's exhaustively mutually exclusive, the sum of the probabilities will always add to 1. Similarly here, you can see that we've exhausted the whole sample space and everything is mutually exclusive. Okay? All the probabilities add to 1. Okay? In this situation here, we've broken the sample space up into two portions, the evens and the odds. There's no other number in the sample space left out. Okay? You're either even or you're odd. Okay? We can see the sum of the probabilities is 1. Now in this situation here, okay, the probability of an even number is 1 over 2. Okay? What set was that event? That event, okay, was 2, 4, and 6. Okay? The probability of a number being greater than or equal to 2, okay, well, the set of the event represented the numbers 2, well, it is 5, yeah, okay, 2, 3, 4, 5, and 6. Okay? Now what we can actually see here is that these two events, okay, share some commonality. The 2 is there, the 4 is there, and the 6 is there. So they're not mutually exclusive. Okay? In which case, well, they're not mutually exclusive, and also they're not exhaustive. We haven't considered the possibility of getting a 1. Okay? Okay? So, but when we don't have events that are mutually exclusive and when they're not exhaustive, okay, the sum of the probabilities won't add up to 1. Okay? just let's keep that in mind. That's an important condition here. Okay. Let's have a look at one final situation. Okay. So in this case here, I'm interested in example. Let's say example 4. Okay. This time we're rolling 2 die. Okay. Now previously we had the sample space. Okay. In one of our previous videos, we developed the sample space for this particular experiment. Okay. And the sample space looks something like this. Okay. The sample space was, well, when we roll 2 die, we could keep track of the first die and the second die outcomes. The first die 1 to 6, the second die 1 to 6. So we end up with a set of ordered pairs. This symbolizing that the first die came up a 1, the second die a 1. This symbolizing that the first die was a 1, the second die a 2. First die a 1, the second die a 3, and so on. We had 36 possible outcomes. So I might be interested in this experiment, in asking the question, well, what's the probability when I roll a die, when I roll 2 dies, that the sum, of the face values that are shown, that the sum is equal to, let's say, 4. In other words, I'm interested in what's the probability that when I roll 2 die, that their sum, is 4. Okay. Once again, this has to be equal to the number of favorable outcomes divided by the number of possible outcomes. Okay. Now, from our sample space perspective, the number of possible outcomes when we roll 2 die, there's 36 possible outcomes. 36 possible pairings, so it's relative to 36. The question is, out of these, how many are favorable with respect to this event? Here's the event. The event is that the sum, when I roll the die, the 2 die, that's what X represents, that the sum is 4. So which ones of these events have a sum of 4? Well, here when we have 1, 3, the sum is 4. Here when we have 2, 2, the sum is 4. And here when we have 3, 1, the sum is 4. Nowhere else in this particular set is the sum of the 2 events 4. So it's along this particular diagonal here. Okay? So you can see we have 1, 2, 3 possible things could happen. So the probability that when I roll 2 die, that the sum achieved of the 2 faces of the die is 4, is you have 3 chances out of 36. So we have 3 chances out of 36, which I suppose is you have a 1 in 12 chance of that happening. We can continue, and I could ask the question, well, what's the probability that when I roll 2 die, that the sum is, let's say, that the sum is 8, as an example. Once again, when you roll 2 die, the sample space has 36 items in it, 36 ordered pairs. So it's relative to 36. How many are favorable? How many add to 8? And well, you can actually see there's no numbers along the first row that add to 8. There is a 2 and a 6 that adds to 8 here. There's a 3 and a 5, there's the 4 and the 4, there's the 5 and the 3, and there's the 6 and the 2. They all sum to 8. So this diagonal along here gives us our possible outcomes, or our favorable outcomes. So we have 1, 2, 3, 4, 5. We have 5 possible outcomes. Okay? Let me ask another way. Let's ask another question. What is the probability, when I roll 2 die, that the first die's number, that the first die, value, divides the second die value. A little bit more complicated this is, Once again, it's a probability, it's a proportion. The number of possible outcomes is how many outcomes could we get when we roll 2 die? And we know, we've already seen it here. We've got 36 possible outcomes. So whatever we get here, it's relative to 36. Now the question we now have is, out of all the outcomes, when we look at the first number, does the first number divide into the second number? Well, let's see. Actually, along this particular row here, 1 divides into all numbers, So 1 divides into 1, 1 divides into 2, 1 into 3, 1 into 4, 1 into 5, 1 into 6. So we have 6 possibilities along here. What about down here? 2 doesn't divide into 1. 2 divides into 2. That's good. 2 doesn't divide into 3. 2 divides into 4, and 2 divides into 6. So we have 3 others here. giving us a running total of 9. What about the next one? You can see 3 divides into 3, and it divides into 6, so we have 2 here. Okay. In which case, what we have is we have 6, 3 gives us 9, and 2 gives us 11 so far. What about here? Well, we have 4 divides into 4, that gives us 12. Okay. 4 doesn't divide into 5 or 6. What about here? 5 divides into 5, that gives us 13. And finally, 6 divides into 6 gives us 14. So there's 14 possible outcomes. Actually, if I was to list the outcomes, okay, if I was to list the outcomes of interest, okay, the outcomes that match this particular thing, yeah, okay, or the events, okay, we're talking about the set, okay, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. We're talking about 2 2, 2 4, 2 6. We're talking about 3 3, 3 6. We're talking about 4 4. We're talking about 5 5, and we're also talking about 6 6. Okay, they're the only atomic events, okay, inside our sample space. Okay, where the first number divides into the second number. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 14 of them. Okay. So this was still a very basic video, okay, and it was dealing with the basic counting rule. Okay, so the basic counting rule. The next video in the series is going to deal with the addition rule and the multiplication rule, okay, which is an extension, which is going to allow us to answer some more complicated questions. Yeah. But once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope this video was somewhat helpful. Okay? Bye bye.